It's really, the talk is mostly about a project we've been working on, but I also want to mention some of the ideas which we've had problems with, which we think the project will lead on to, which is where the data staging aspects really come in. The project's a Framework 7 FET project called NextMuse, Next Generation Multi-Mechanics Simulation Environment. I was very impressed by the EU because they said because it's an FET project, failure is an option, which I want you to bear that in mind throughout the rest of the presentation. The partners we're working with are doing particle simulations. They're interested in ships. They're actually branching out to do things like wheels and doing a conventional modeling of CFD on these kind of treads and things is quite expensive, but with particle methods, because you only have to represent the boundaries, it makes the job much more tractable. In particular, ships, they're interested in, the ship is sloshing, and if there's a tanker of oil or something on top of the ship, and that's sloshing in its own frame of reference, and the ship is then being disturbed by waves, how do these couple, how do they interact? And if you move things around, how does that change? And what they'd really like to do is they'd like to use the computing resources as an interactive tool, so they can have the ship and push it left and right and see the graphs change and then change something and read, and they don't want to run things as batch jobs. They want to actually work like engineers where they're testing a harness, they're running in real time. Another project, another partner I should say, is working on heart valve design, and they're really interested in if you model the blood flowing through the valve, are the red blood cells basically ripped apart by the stresses as they pass through? And if you change the shape of the valves, and if you add a chamfer here, if you move them there, how does that change? And could we have a knob that you can pull which adjusts these kind of things and they can see the stress being plotted on screen, that kind of stuff. And from our point of view, the most interesting one is these Pelton turbine people. We've actually worked with these people in a lot of projects over the years, and they, I'm hoping this there should be an animation, but I guess, oh, that's a shame. I wonder if it plays if I do anything on here. Okay, well, what you should see is the bucket turning round. Over here you have jets. Water comes down, there's a lake on the top of the mountain, the water comes down a pipe, it comes out of this jet here, hits this bucket, and then it splashes out. Now the buckets all spin round, and the shape of this jet actually plays quite an important part in the momentum transfer, the energy transfer into these buckets. And these wheels are actually usually mounted in a horizontal frame of reference, so they spin like this rather than like a wheel. And what happens is the water splashes out, and this casing is all basically sealed. And when the water splashes out, they can have as many as 6 jets all around here, and if the water comes out there, splashes, and then lands on another jet, it disturbs the flow, which in turn causes the jets to spray out, which you lose momentum. And even if you only lose a fraction of a percentage of the energy, it's actually megawatts that they're talking about over a period of months and years. And so what happens is the water comes splashing out, and it comes all over in this region, and what they want to do is put little plates in to just deflect the flow. And they'd like to be able to just move these plates around and see how the flow changes as they're doing this. So what they really want to do is play with the designs. Instead of running a batch job, seeing the results, plotting them out, then submitting another one, they want to just play with the stuff, which is where the project really is going. So we have requirements. We want to in-situ visualize their simulations, but we want to actually do computational steering. We want to potentially take all the particles on the mesh, move them a bit to the left, and then send them back into the simulation to change something fundamental. We don't just want to send a parameter alpha, change it from 0.2 to 0.3, which is some velocity factor. We actually want to be able to change a whole surface, move it around. Because they only deal with the surface meshes, and you don't have this complex FEM model where you have all the interacting tetrahedra, it's actually much more tractable to do. We can consider doing it. So potentially, I beg pardon, wrong button, large data, two-way. And some of them are Fortran, some of them are C, some of them are C++. We've got different codes to work with. And they really, as I said a moment, they really want to treat their cluster or their supercomputer just like it's the workstation. They don't want to have to worry too much about all these things that we deal with every day, but they don't know much about. The constraints being the partners, they're all located around the world. And they're really physicists, and they don't know an awful lot about really good programming techniques. So they want to have as simple as API as possible. They want to just say, just give us something that works, let us play with it. When it breaks, we'll ask for help, that kind of thing. In the ideal world, you'd run your simulation on a whole bunch of cores, you'd link all the visualization and analysis code directly to it, everything would just be coupled together as one huge great MPI job, and it would all work very nicely. And Visit and PowerView used this for in-situ visualization. This scared us at the start of the project because some of the visualization stuff just doesn't scale as well as the simulation might do. And if you do this, you may effectively destroy the simulation by putting bad analysis into it, effectively. And so what we really wanted was, rather than breaking the simulation, is to have a more loose coupling where, if you're familiar with parallel file systems, the simulation writes out to OSS nodes. This is a Lustre example. GPFS is basically the same, which then gets sent off to disk. And we said to ourselves, well, if we were to just replace those OSS nodes with distributed memory nodes, DSM there, which is our data staging area, instead of writing to disk, we could just write to some memory area, which the simulation and the analysis can connect to. And in this case, we have the viz nodes over here, which are connected to the DSM. In fact, this green box means that these DSM nodes and these viz nodes are actually the same. Or alternatively, you could have the simulation hosting these memory nodes and you could have them the same. So it's sort of flexible in the sense that you could have the simulation allocate a memory buffer and everything works from that. Or you can have the analysis allocate a memory buffer and everything works for that. And they're both distributed and you can kind of choose what you want. This is what we refer to as a loose coupling model because we haven't physically linked the two applications directly together. We're coupling them using an MPI type of approach. And in fact, we use a com publish, com accept, so you can dynamically connect. And some of the advantages of a loose coupling are that you can have, for example, a simulation machine up here connected via either an InfiniBand switch or if it's on some other network, to an analysis machine. And then because we're using a PowerView client-server framework, we can have the GUI running on your workstation, we can have a viz cluster doing this, and we can have the big Cray doing that. Or we actually find that this is the one we use all the time. We have the Cray, for example, doing simulation and analysis, or the viz cluster doing simulation and analysis, and the workstation on the desktop. And you could even have all of this going on just on the desktop and this. In fact, you could do the whole thing on just one machine if you want to, but I didn't bother including that. It's kind of flexible, and as long as you've got a network connection between them, you can do it whichever way you like. When you actually use our implementation, where I think I probably skipped a couple, actually. I cut some slides out from my original presentations. HDF is where we came from on this, is that we told all our project partners years ago, before this project even started, we were working with them on other things, and we said, look, use HDF, it's great, because you can write out in parallel, the files are easy to use, and this is what kind of led us into this world. Now, it turns out that HDF has a rather simple interface which allows you to basically strip out the file driver layer and replace it with your own driver layer. So that normally when you use HDF, you say, create a file, and you create a property list, which is how you access the file. And when you're using Parallel, you use an MPIO. So you say, give me the MPIO-based file driver, and then you write out, and it all goes through MPIO. To use our stuff, all you have to do is literally replace the file driver with what we've called our I'm looking at the wrong line. You insert a DSM file driver instead of an MPIO driver. It's basically one line of code changes, and then instead of all your data going to the disk, it goes into our memory buffer. And from that point of view, it satisfied our main requirement at the beginning, which is we've got these Fortran people, these C people, they're physicists, they don't know anything about a simple API. They really only have to make one line of code change, and all their data just goes into our buffer instead of the disk. We've completely bypassed all the MPIO, all the Lustre striping, all of that stuff. Just forget about it. And then you just carry on. You create a data set, you write into it, you create your normal property transfer lists. I won't go into the details there. And the file driver itself is, you have nodes where you've allocated memory. In this graph picture, we've got 4. And you open the file, you write stuff into it, you close the file, and then the analysis can open the file and it can query it. Now, the more nodes you use, the more links on the network you're likely to be using. In this case, we've got 4, and if it's on the viz cluster, it's 4 links. If it's on the Cray, then it's 4 times by 3 dimensions, because they've all got links to different things. And how you actually send data into these depends on which machine you're using. And we have layers, basically a communication layer, which is like a plugin. It's a C++ class, and you can create your own ones. And we have a TCP, MPI, a one-sided MPI, and a DMAP, which is the distributed memory application one, which runs on the cray really close to the hardware. And I should point out, the more links that you're using, the more bandwidth you're likely to get when you write data into it. Now, when you create an HDF file, and this applies to any file, but we'll just talk about HDF here, it's basically you allocate a bunch of space, and then you write data into the space. And if you allocate, let's say, a 1 gigabyte memory buffer, and then you write 1 gigabyte of memory into it, then everything's lovely, because what you're effectively doing is you're sending all of these parallel tasks up here. Let's suppose your simulation's running on 512 or 1024 processes. It's all being written through different links into these 4, and because because you're filling the memory, you're using all the links in the network. And so I should point out there's metadata here, which is the sort of how HDF manages what's in the data in the file. When you write into it, you fill up the memory, you use all the links, everybody's happy. But actually, most people don't do that, because you open the data, you open up the file, and you write lots of small data sets into it, usually, rather than one enormous one. Now, if you do use the whole file, on, for example, the InfiniBand cluster, we get, can anybody read these numbers? I'm suspecting no. They looked better on the screen, but they look a bit too small up there. On a small cluster, if we have 4 nodes holding 4 nodes each with 4 processes, allocating a DSM, we write into it, and this, I think, says 10 gigabytes per second. So you open up the file, you write into it, you close it, and you get about 10 gigabytes per second because you've basically used all the links. On the cray, we're getting about, gosh, I can't read these numbers at all. It's about 40, 50, peaking up somewhere around 60 gigabytes per second, using 160 processes, 40 nodes. So we've effectively got 40 links, or 40 Gemini sockets effectively active. And so we're getting pretty good bandwidth in the sense that we've got a whole bunch of, I forget now how many, is that 2048 over there? I can't see the numbers. 2048, I think it is. Host process, the simulation's running on 2048, and it writes into that, and it basically uses all the links that are available, and you get a very good bandwidth. The problem is that you normally don't do that. You actually write out one array, like pressure, then temperature, then velocity, and in a sense, you've serialized your I/O, because what you do is you go, dataset create, write it out, close that dataset, dataset create, write it out, close that dataset. You've kind of serialized things, and what happens is all of the pressure is going to this memory area here. All of the temperature is going to this. All of the velocity is going to here. And you're only now using a subset of the links. So you're not going to get the bandwidth you thought you were getting initially. And a very simple solution to this is to just not have a linear address mapping here. This flat linear address space. Unfortunately, HDF only gives us a linear address space. But there's a way around it, which is that we can skip the animation, you can guess what's happening, is to, instead of mapping the HDF memory to our DSM memory, we can insert a layer in between, which is like a virtual address layer, and we can add in like block cyclic or random block allocation, so that instead, when you write the pressure array, it's split a piece here, piece here, piece here, piece here, the next piece here, next piece here, next piece, and then the temperature. Now what we've done is we've split the data, fanned it out, so that we're now using many, many more links. And when we do that, we find, these are some micro benchmarks, I'll come back to those in a second. When we do that, we find that if we write out just a linear memory, but we write lots of small data sets, we get a comparatively low, this is a two-sided MPI, and that's a one-sided MPI, and that's I beg your pardon, this is a DMAP. This is the DMAP communicator, the green one. You find now the same conditions, we're getting 60, 70 gigabytes per second into our DSM, even when we're writing out lots and lots of small data sets. In this example, we're writing out 10. And in fact, these graphs here are actually the result of doing lots of little micro benchmarks where you say, well, let's have a block of 1 kilobyte, 2 kilobytes, 4 kilobytes, run lots of tests, and you generate all series of graphs and think, okay, the best one turns out to be. And you see exactly the same little drop points that Professor Panda showed us earlier, where you switch from the small, the direct memory copies to the buffered memory copies inside the MPI layer and also inside the Gemini layer. Oh, I'm going the wrong way, I'm sorry. So the bandwidth is really nice, and bear in mind that here we're using basically 40 gig DSM on 160 processes. If we doubled it to 320 processes or 500 processes, then we expect the bandwidth to scale pretty much linearly because we're just saturating the network with these little blocks of data going out. In principle, if we took the machine and we said half the nodes to be senders and half to receivers, we think we'd get pretty close to the bisection bandwidth of the machine. But actually placing the nodes in exactly the right way so that you were modeling exactly along one X, Y, or Z plane, we haven't actually done it. It's worth comparing that other people are doing very similar things. And there's a package out there called Data Spaces, which is being developed by Rutgers and Oak Ridge. And theirs is different in many ways, but the basic concept is the same in that you have memory, which lots of people connect to. They write stuff in and they read stuff out. By using HDF, what we've actually done is we've kind of circumvented. We've said, HDF, here's a data set. When you write it into the file, HDF does all the generation of the memory addresses for us, in the sense that what they effectively do is they use hashing functions. Say, here's an array, which is n dimensions, or here's a space-filling curve, which you can map to one dimension, and this piece of the array is going to be sent into this region of data, this region of the file, and there's a quite complicated layer of logic in there which maps pieces so that if 1,000 processes are writing chunks in, each gets allocated different bits of memory and they write it to there and write it to there. HDF basically does all that for us. It is a file system in its own right. It manages all the addresses. The only downside is that we can only use this linear address space. And of course, we only support 2 connections at the moment, and not completely simultaneously. The graphs I showed you a moment ago are basically benchmarks. One of the solvers we're connecting to is called SPH-Flow. And one of the examples that we use is a wedge which is dropped into the fluid and it sort of sloshes around. When we connected this up to the DSM, we found that if we measure the disk I/O, scaling it from 1 to 1,000 processes, and we just integrate the total time it uses to write to the disk, we find that it comes out like that. If we replace it with the DSM, it looks more like that. This is a log scale. So it's almost 2 orders of magnitude better. So down here, we're getting 200 gigabytes per second, and they're getting 2 gigabytes, roughly. And as a comparison, the total CPU time that they're actually using, I should say that this is a reasonably weakly scaled example, because the code only runs effectively if you have a minimum of about 50,000 particles per core. So when you're running on 1, you're doing 50,000. When you're running on 1,000, you're doing 50 million or whatever the numbers work out as. So what you're writing out is, you're writing out 200 gigabytes here. You're only writing out 200 megabytes here, effectively. But what's happening here is, everybody knows, I mean, half the people in the room seem to work with I/O companies, is that basically the disk I/O isn't scaling here. And actually, this is not a very fair test, because you wouldn't write the stuff out every single time step. But actually, with our DSM, you basically can, because it's all just memory-to-memory copies. And the turbine people, for example, how does it look when we use it? Well, essentially, we've bolted everything into a PowerView interface. You start the simulation. In fact, we've made it so that when you connect up here, you can basically click a button, you can submit a Slurm job onto the thing, it launches the solver, it launches the DSM host, they connect, everything connects back to the PowerView, boom, and you instantly get it. The interesting thing is that visualization is very, very easy, because they write into an HDF file, and you just read it out. You don't have to do anything. You only make one line of code change to the solver to say, use our DSM. Visualization is very, very simple, as long as you know where to find things in the file. And actually, HDF is supposed to be self-describing in the sense that it tells you what's in its file. I find it a somewhat strange way of describing it, because HDF is the most horribly complex file thing. You can store anything in any combination. You can have pressure arrays, temperature arrays, geometry arrays, topology arrays. They can be all randomly placed. So what we do is we make the, oops, I beg your pardon, we make the guys write a little template file which basically says, in the HDF file there's a fluid group, and in that there's position, there's density, there's velocity. As long as we know where those are, then we can read those arrays out, we can map them to geometry, and we can display them on the screen, everything's happy. It's not so easy when you want to do computational steering because we can, I made a deliberate spelling mistake up there, just in case you're worried. When you do steering, you want to write things back into I should point out that because